3 like they do on TV?
Go ahead, sir. You got it.
All right. Well, good evening, ladies and gentlemen and others.
Wow.
For those of you that don't know me, I'm Ken Goodson, KA5KXW. My bona fides, I've been a ham as long as I can remember, about 40 years now. And I generally end up teaching this section of the course, and it's a little easier this time since we're just doing tech and not tech and general. Generally, by the time you get to this point in the course, you're starting to wonder whether this is all worth it. And let me assure you that it is, and that you may be tempted to think that you have to memorize all. I generally end up teaching this section of it. But that's not the case. What happens once you get past your test, you'll find that you really learn how to be a ham after that. It's a lot like getting your driver's license, that you can go through driver's training, and there's no way you can cover all the possibilities, and there's so much that gets left out. But once you actually get on the road, you find that it's pretty easy after a short while. So you can think of it the same way here. Let me encourage you to do as much online testing, practice tests as possible, because once you get about 80% or 85% on those practice tests, you're ready to test whether you've listened to me or not. So I encourage you to do those early and often. Are there any questions of those of you who have already read through the material on this? Are there any stump the chump type questions that I need to emphasize later on in the class?
I don't think so.
Well, I've got to read it all 3 more times. I've got to read it all 3 more times. It's like Greek.
Yeah, a lot of it is Greek, as a matter of fact.
Well,
and we'll get to that shortly.
Good. I'm right.
All right. Yeah,
Says the lawyer in the bunch.
Right.
Nerd. Go
Well,
to the nerd.
without further ado, let's just slide on over to the first slide. This is the 3A section on electricity. And radios, of course, exploit electromagnetic waves to communicate. And what radios actually are forms of filter that allow you to select just a little slice of the entire electromagnetic spectrum to gather some intelligence, whether that's through Morse code or through voice or all of the many digital modes that are out there. That's really the basis of what a radio is. And of course, they're energized and powered by electricity. And we'll go through tonight some of the components that make up the radios, a little bit about how they fit together, and then we'll talk a little bit about kind of like building blocks. We're going to start really small, and we'll get into some bigger modules as we go along. Electricity is fundamentally the flow of electrons from one place to another. There are electrical charges that are positive and those that are negative. Positives are, if you can remember back to your middle school physics class, that neutrons and protons make up the center of an atom, and the proton is a positively charged entity, and an electron is a negatively charged entity. And the movement from one place to another is actually the flow of electricity. Electromotive force we think of as coming from a battery or a generator, and in real terms, the socket in your wall is a source of electromotive force, where we can harness that flow of electrons. The 2 main quantities that we talk about with electricity is current and voltage. Current is symbolized by I in these formulas that you see in your book. And I've never gotten a satisfactory answer of why they chose I as a symbol for current. C was already taken. So I think that's how they ended up with it. The mnemonic that I use is instantaneous charge, is how I think of, or instantaneous flow of electrons. Current is actually the movement of electrons past a certain point. Current is how fast those are moving at any particular time. Voltage is the total quantity of force that's available, and current is how fast they move. You can use the water analogy, which is commonly used, and in that regard, voltage would be the container of water. And the larger it is, the more voltage is available. And the speed that the electrons move would be the current. It's just like a river. A faster moving current would be a greater current. It works the same way in electricity. So current is measured in amperes, usually abbreviated to amps, abbreviated A. And that's analogous to length. The unit of length could be inches or meters, and symbolized by L in a formula. Voltage is the amount of electromagnetic force, or the amount of electrons that are available to flow, not the ones that are moving, but those that are available to flow. And that's electric potential. Again, the unit that we measure it in is volts, and it can be either E or V in formulas. Try to stick with E. I think that's typically used with DC, and you'll see V used in AC. And we'll get to the difference between those two in just a moment. Now then, if you're sticking with that water analogy of water through a hose being the same thing as electrons through a wire or through a conductor, anything that impedes that flow is resistance. And the symbol is a bit of a squiggly line. And you can think of that, those little kinks in the hose is slowing down that flow of electrons. The measurement of resistance is ohms, and the symbol that we use in our formulas is always going to be R. And we'll see those when we talk about Ohm's law formula in just a minute. What a resistor actually is a device that converts electricity into something else. It can be into heat, could be into light, but its whole goal is to limit the flow of electrons. That's how it's useful to us. You can think of it like friction. There's a concept with water called laminar flow, where if fluid is going through a pipe and it's all moving, all the little particles in the water are moving exactly parallel to the outsides of the pipe. We call that laminar flow, and there's very little resistance. But as soon as you kink that pipe, that destroys that laminar flow, and you get resistance. It's the same thing with electricity, and we call it resistance. There are conductive materials, and there are insulating materials. Those that don't impede the flow of electrons we consider to be conductors, and those that allow no current flow to flow at all are perfect insulators. They have a very high resistance. We're doing good so far? I got thumbs up. Okay. Okay, electrical concepts. This is a really good slide. Again, it's showing you that water analogy again. On the left-hand side, you see a pump that is creating pressure. Pressure being the analog to voltage, flow being the analog to current, like current flow. If you keep that image in mind, if you can imagine any type of a kink or reduction in flow, would increase the pressure and would limit the flow. So that's something to keep in mind as we move along. It's a good little slide to keep in mind, though. This slide also, if you look over on the right-hand side, you see there's two meters there, symbols for meters. One is a voltmeter, one is a ammeter or a current meter. And if you'll notice that to measure voltage, you have to go across the power source there. You could take the voltmeter away and you would still read current over on that side. However, if you look on the right side where there's the ammeter, you'll notice that it is in line with the circuit. If you remove that ammeter, the current would stop flowing. So when you're using a voltmeter in practice, you can apply your leads from your voltmeter across a voltage source and get a result. If you apply your leads across the same way with that ammeter, you won't get any reading. You have to be in the circuit itself for the current to flow. We'll see why in just a minute, but that's called a series circuit right off the bat. Okay, moving on to the next slide. Two kinds of current. We talked a little earlier about direct current usually being symbolized by E. Well, current that flows in only one direction from positive to negative or negative to positive is direct current. And that's most generally created by chemical means, which is a battery. It can also be made by rectifying AC voltage by taking one of those directions away from AC to create DC. Household current is AC primarily because it's easier to transform voltages with AC, and we'll see why in just a few minutes. But just for now, you can see in the graph to the right, they're actually showing you three different types of wave. On the right-hand side, right above the letter A, you see where it says steady direct current. That could be on its own graph. It doesn't change with time. It stays constant as long as the circuit is completed. The upper part of that graph where you see the pulsing direct current, that is showing you DC through time as if someone were turning a switch on or off. At the first instance, you see that it has a magnitude that is above 0, and then it drops down to 0, like somebody shut off a switch. And then it comes back up again, and then it decays back down to 0, and then it comes back on again. It'd be like somebody turning the switch on and off to interrupt the DC. We call that pulse DC, but it's still DC because it never goes below that 0 limit. It stays, in this case, if you look at the top of the graph, is positive. It never goes below 0, and it always stays positive whenever it's on. So it's still DC, even though it's pulsed on and off. Okay, if you look at the bottom of that right-hand side, where you see a lovely little sine wave there, as you go through time, the wave goes to positive, then down to negative, then up to positive again. And there's a reason for that. When we're talking about household current, I know last week that Ron talked about if you passed a current through a coil of wire, that a magnetic field was generated. We remember that? Yes? Okay, the opposite is also true. Whenever you pass a wire through a magnetic field, it generates a voltage in that wire. If you think about a generator, like on a car or even a utility generator, where you have a spinning armature and a north pole and a south pole on either side of that big coil of wire, as that armature spins, the polarity of the magnetism changes for the wire that's spinning in that magnetic field. That's how you end up with that sine wave for power generation. Does that make sense? Okay. Okay, AC current reverses direction on a regular basis. The difference when it is passed through zero twice, that's one cycle. So if you look at your graph on the lower right, you start at the zero origin point, you go positive, you pass through zero back to negative and back to zero again. That one cycle from zero, positive, zero, negative, and back to zero again, that's one cycle. So your graph here is showing us what, 1, 2, 3, 3 complete cycles. If our time series there was 1 second, then what you would be looking at would be a 3 Hertz wave. Old timers may remember that we didn't bother with talking about Hertz. Everything was measured in cycles per second, like it should be, by golly. And but Hertz is the measure of frequency. All right, let's talk about beginning basic circuits. A circuit is not complete until there is a path from a voltage source back to the voltage source. Okay, that's the complete circuit. Using that water analogy, if you want to go back to that previous slide, where you see that on the pressure side, the fluid comes out, it passes through the flow meter and then returns to the pump. Same thing is happening with the battery on the right-hand side. We have electrons leaving the negative, well, leaving the positive terminal and returning to the negative terminal. I'm going to give you a little aside here. This is free. You don't have to pay for this piece of advice. There are 2 ways of looking at electrical or electron flow, and engineers and scientists have argued about this forever. They're both wrong. Conventional flow shows that electricity leaves the positive terminal of the battery and returns to the negative terminal. We also talked just a little while ago about how electrons were negatively charged. So electrons flow from negative to positive. Well, engineers say that it goes from positive to negative, and that's called conventional flow. And then the smarter scientists say that it goes from the negative terminal to the positive, which is the electron flow model. They're both just models. Whatever makes sense to you is perfectly fine to use, but just know that both of those exist out there. So don't get confused or let it bother you any when sometimes they'll say that we're going from a higher potential from positive to negative, and then somebody else says, no, 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 it goes from negative to positive because electrons are attracted to the positive terminal. It's the same thing, and these are all just models that we use just to make sense of things. But back to the point, a circuit has to pretty much end up where it starts. And in this case, we're leaving the pressure side, we go through our load and then back to the pump again. That's a complete circuit with fluid. With electronics, we're leaving the positive terminal of the battery down through our current meter and then back to the battery again. So we end up basically where we started, but that's what completes the circuit. And anything that breaks that creates an open circuit. Let's go back to where we were, if I can. There's 2 types of electric circuits that we're going to talk about, series and parallel. And the easiest way to remember it is that in a series circuit, each component only shares one connection. In a parallel circuit, they share 2 or more connections. Here's an example of a series circuit where we leave the positive terminal of the battery. We go through these resistances. In this case, these are lovely little light bulbs. And you can see that the current that leaves the battery flows in turn through each of the three resistances. So if you put an ammeter at this point right before resistance 1, whatever reading you get will be the same reading that you would get right here in front of resistor 2. It'd be the same reading that you would get right here at resistor 3, and it would be the same reading that you get returning back to the battery. It's not exactly the same electrons, but it is the same flow through all three of these loads. What's the downside of this? If any of these loads fails, then the whole circuit fails. Okay, think of your water analogy. If this were a valve that were suddenly opened and all the water dumped out, there'd be no flow remaining to go on to the other loads. So that makes sense? All right. Okay, parallel circuits share 2 or more connections. And you can see here that you have a battery, and the connections to the battery are shared through all 3 loads here. Okay, where in a series circuit, if one of the bulbs failed, they all fail. In this way of doing things, if one of these loads fails, there's still a current flow that is able to reach the other loads, okay, because they share both terminals here. Now then, if you put an ammeter here, you could measure a current here, and if all 3 of these loads are equal, each branch would have 1/3 of the total current. Sensible? Okay. So the current is, excuse me, the voltage is the same for all 3 of these, but the current is different. Back up to the series circuit, the current is the same for each one of those, but each one of these loads will drop 1/3 of the voltage as it goes along. So if you had a 9-volt battery and each one of these bulbs were rated for 3 volts, you'd drop 3 volts across here. So your meter, if you put a voltmeter across here, you would measure 3 volts, 6 volts, and then ultimately 9 volts. Okay. Moving along. Ohm's law. Anybody dreading Ohm's law? No? Good. Ohm's law is pretty simple to remember if you think of it as a relationship. Math is just a language to describe things. Ohm's law describes the relationship between voltage, current, and resistance. You have some questions that'll be on your test. I think there's like 1. So if you didn't learn this at all, you're still good. But if you know any 2 of the units here, then you can derive the third by using the simple formula. This little circle here is a little mnemonic to help you remember. If, for instance, you were trying to find the current through a resistor and you knew the value of that resistor and you knew the voltage, you could just cover up the little I with your thumb and see that E over R is going to equal the current that you're looking for. Same thing if you were looking, if you knew the current and you knew the resistance, you can put your thumb over the E in your little circle there and see that it's I times R. Is how you find the missing value. Some people draw them as a pyramid or a triangle, which makes more sense to me. But it's just pointing out the relationship between voltage, current, and resistance. The higher the resistance with voltage being fixed, then the smaller the current. And you can take a calculator and work through some of those. In fact, after this, I've got a nifty little simulator that is an online simulator that you can play around with these values and see how it actually works. But for now, just remember E equals I times R, and then you can set it up in this circle to help you find that missing value. But you have to know too. All right, power. Power is the rate at which energy is consumed. It is really measuring the conversion of electricity into something else, whether it's heat, light, whatever. The resistance from the devices that we use is what determines how much power is consumed. It's measured in watts. For some things, kilowatts is the unit that you'll see most often. It has its own little circle or triangle, and the relationship looks very similar to the other. Well, the other was I times R. Now we have I times E equals power. So again, if you're looking for any one quantity, like if you're looking for E, put your thumb over it and you can see that power over current is going to equal to voltage. And we'll go over why this is useful shortly. Metric prefixes. I don't know an easy way to remember all these except just to use them. The ones that you'll see most often, I think, on your test are of course going to be kilo and mega, because when we're talking about frequencies, and milli and micro and pico are the ones that are used most when we're talking about electronic components. Very small values. Pico, that's 10 to the negative 12th, which would be a millionth of a millionth. So it's a very small quantity. Hams do have frequencies that go up into the gigahertz range that we're allocated, although I don't think it's used a whole lot. Our buddy Phil can tell you a lot more about that than I can. He is the radar man. Electrical units. The ampere, we talked about that as the measure of current. Coulomb is the measure of charge. Not used a whole lot in amateur radio circuitry descriptions. Farad, after Michael Faraday, usually picofarads or microfarads is quantities that we'll use in electronics. Same thing with the Henry. Microhenries and millihenries are what you see most often in circuits. Hertz, when you're talking hertz, you know, the low frequencies are audio, and then kilohertz and megahertz is when we get up into radio frequencies. Ohms, our measure of resistance, watt and voltage. And they give you this slide, but I don't think there's a single question on how volt got its name, oddly enough. And extra points to anybody that can actually say Volta's full name 10 times fast. All right, moving on to electric components. What we're trying to do with an electronic circuit is to take, or with a radio rather, we're trying to take a slice of the electromagnetic spectrum and pick out from it what we want to choose to get some information. And we do that by using a bunch of little devices that change current, manipulate current, stop current, the components that we use to do that are capacitors, inductors, resistors, those sorts of things. And we'll get slides on those in just a second. A schematic diagram is it's kind of like a blueprint for an architect. It has standardized symbols for each of the electronic components so that we can have a shorthand that we all understand to put these circuits together. And each device has a different symbol. Here's a general schematic diagram. And you can see the different types of things that are on here. This little symbol here with a positive and negative and the two plates, that's a battery. The little dots that you see, these denote a connection between different devices. So if the black lines that you see here, these represent wires or connections, and the little dots are what show an intersection that actually connects. It's not shown on this diagram, but you will see instances where two lines may cross each other without having the little black dot. And if they do cross without the little black dot, that means they're not connected. And there's several different standards of drawing that. Sometimes they put a little hump over the top of it to show that it's not connected, but just drawing a line across works if it doesn't have that little black dot. But resistors here and here, again, if you think back to that water model of current, and you think of this as a hose with a lot of sharp kinks in it, it's going to limit the current flow through there. So that's the symbol for resistor. There is a picture of a resistor there. This kind of dates whoever made these slides. It wasn't me. That's commonly what you would see for a resistor from 40 years ago. They're still available like that. That's a carbon composition resistor. And in size, they range from something as long as maybe the diameter of a dime up to an inch, and a diameter that's probably an eighth of an inch. Nowadays, everything is surface mount, which are tiny in comparison. But anyway, the function of the resistor is again to limit that flow of current. The schematic symbol is a little squiggly line that you see, and the potentiometer that is shown on the right is a variable resistor. You can see that it has three terminals, 1, 2, and 3, and this third terminal moves along the resistive material so that you can vary the amount of resistance that it has. Think of a volume control on a TV, at least the old ones that actually had a knob, not the button style. Those are potentiometers, things that you turn. Ohm's law, again, has resistance as one of the values that you need. And these are available in a wide variety of resistances. The funny little bands that you see here determine the value of the resistor. The fourth band here, the little silver one, shows the tolerance of the resistor. The tolerance is an engineering term. There's no such thing as a perfect component. Manufacturers have a lot of variance that creeps in through the building process, and they will denote what the tolerance is for just about any component out there. A 10% tolerance would mean that from whatever value is marked on here, that you have a plus or minus 10% leeway in what that value actually is in the real world. So again, when we're talking about all this, we're talking about models anyway. It's not exactly the way it plays out in real life, but it's a good approximation. It's a model of how things work. A capacitor. A capacitor is, I think Ron talked last week about an electric field and how an electric field can be built up between two plates. I don't know if you remember that discussion. The capacitor is a pretty handy little device. It turns out that it has a property that is similar to a resistor in that it resists a change in voltage. What does that mean? Well, it means that with an electric field built in between those two plates, that it acts like a little tiny battery. And it stores that electric field between the two plates. At the bottom, you see where it's talking about an insulating dielectric material. What the heck is that? Well, it turns out that most materials that are not conductors have what's called a dielectric constant, which is its ability to impede that electric field from forming. Something that's a very good dielectric would mean that you have a greater value than the one that's not such a great dielectric. But they're very good, and what we use them for in radio is that they block DC current. A DC current can't pass through it because it gets there, it builds up its electric field, and the current stops. AC current, however, can pass through it. But its biggest contribution is it opposes a change in voltage, and it blocks DC. And we'll see how that's relevant here in just a minute. They're used in filters quite a lot. Inductor. Again, taking you back to last week with Ron, a coil of wire with an applied voltage through it creates a magnetic field. And that happens with inductors. It stores that energy for a short period of time. And the very useful feature that it has is that it impedes a change in current. Remember, I said with a capacitor, it resists a change in voltage. The current of the inductor is different. It resists a change in current. Okay, so whenever an electric charge or an electric current is passed through a coil of wire, it generates a magnetic field. When you turn off that voltage source, that magnetic field collapses, and a current flows back through the conductor until it reaches its 0 point again. Well, what's a transformer? It's basically two inductors stuck together. If you look at it, this represents a coil of wire here with some magnetic material here in the middle that we'll call the core. It's usually laminations of iron in this type of transformer. And then we've got another inductor here. Now, we talked about earlier that whenever you pass a current through a wire, it creates a magnetic field. And that in the case of a generator, if you pass a wire through a magnetic field, it generates electricity. Well, we're doing the same thing here. We're inducing a magnetic field into this side, which is creating a magnetic field that covers the whole area here. Once this field is generated here, it is passed on to the other side. Okay, and when this magnetic field collapses over here, this magnetic field on this side collapses. So two different circuits, one that is supplying current and one that is receiving current, it passes through. Now then, if the ratio of the wires between the two sides are identical, then it's a one-to-one transformer, and any voltage that is induced on this end should show up on this other side. Now then, not a perfect component. There'll be a little bit of loss, but that would be a one-to-one transformer. The reason why that we have AC that comes out of our wall sockets is because AC is it's very convenient to change voltages with AC. Imagine, if you would, that you created a magnetic field with a DC circuit on this side. We would charge it up, it would create a magnetic field, and that's it. There wouldn't be any energy transfer between the two. But with the collapsing magnetic field being carried over to the other side, that's how we get the transformer action. You can change the ratio between the two sides and have more turns on one side than the other. If the greater number of turns was on this side, excuse me, if the greater number of turns is on this side, we'll call it the secondary, then that's a step up transformer. And for any voltage that we induce on this side, it'll be greater on this side because of the greater number of turns in the secondary. Out there on your utility poles, it's not unusual to have a 19 kV line bringing electricity through your neighborhood. And of course, the things in your house require 120 volts. Well, they use a step-down transformer to convert that 19 kV down to 120 that you can use. Moving along. Okay, I think we've already talked about resistance. Farads, of course, is the measure of a capacitor. Henries for inductors, and again, microhenries and microfarads are the units that we'll most likely see in radio circuitry. Component designators. When we're looking at that blueprint, that schematic, there's a designator, and it's easier to explain when you have an example. But in most large circuits, you're going to have multiple devices. You may have 100 resistors or 100 capacitors and multiple inductors. To keep it all straight, each one has its own designator to kind of simplify the view. And then there will be a parts list somewhere that says, for example, this 10th resistor that's R10, there will be a parts list somewhere that says R10 is equal to 1,000 ohms. It may be C1 is equal to 1/10 of a microfarad, or an inductor L3 is 0.68 microhenries. It's just another part of the shorthand that we use. Indicators and displays, these are all around us. LEDs, I think, is probably 90% of what's sold or more. But you've seen the symbols for a light bulb. We'll see the symbol for an LED in just a minute. They're just there to communicate some status that we need to know about. I think in my shack, I counted up, there were 22 LCD screens. They're ubiquitous everywhere you turn. Kind of weird to bounce from that to reactance. But when we talked about capacitors and we talked about inductors, we talked about them resisting a change in voltage for capacitors and resisting a change in current for inductors. That resistive action is reactance. And why don't we use the word resistance? Well, reactance is more implied by AC circuits or AC current flow. So capacitors have naturally capacitive reactance. That's their resistance to the change in voltage. And inductors have inductive reactance. And again, that's how it resists, or the measure of how it resists a change in current. And they're complementary. And what that means is that they have opposite sign in math. And we'll see that play out here in just a minute. And it also has a curious little thing that we'll talk about later, is when capacitive reactance equals inductive reactance, they cancel. And we call that state where they cancel resonance. And resonance is very important in radio. Impedance is when you add together, well, I shouldn't say add because it doesn't necessarily add, but when you combine resistance and reactance together, you get impedance. And impedance can be completely resistive, and you'll see that your radio will be rated at 50 ohms output, and that means that it puts out its maximum amount of power when its load is 50 ohms resistive when it's but impedance represents both the components reaction to AC current and also DC currents together. Resonance. Okay, we talked about how radios are nothing but fancy filters. Reactance actually depends on not only the value of the component, but it also depends on the frequency of the AC waveform that it is working with in a circuit. Reactance, inductive reactance, as frequency goes up, so does the reactance. With capacitive reactance, it's the opposite. As frequency goes up, the capacitive reactance goes down. So whenever XL and XC are equal, that's the resonance frequency. And when a circuit has only resistance, that is the point of resonance. Okay. Yuck. That didn't turn out very well. If you look at the diagram on the right, it's incomplete. This gap here, let me change pens. This gap here should have a capacitor right here. At the point where the capacitive reactance of this capacitor equals the capacitive, or excuse me, the inductive reactance of this inductor, we're at resonance. And all the reactances that cancel out means that you have a maximum current flow through this circuit. If you can imagine a point where XC is 0 and XL is high, you wouldn't have a maximum flow. Same is true if XC were high and XL were low, you still would have a limited current flow. But when they equal together, or if they're complementary, one's positive, one's negative, and they equal 0, then your current flow would be maximum through this circuit. Interestingly, if you measured voltage from here to here, voltage would be at a maximum between the two. Now then, you can imagine if there's a 0 point here for frequency, or pick a frequency where these two things are equal and you're resonant. Anytime you get on either side of that resonant frequency, your reactance goes up. Your opposition to flow through the circuit goes up. So what you basically are doing is filtering for the resonant frequency with this circuit. I just pointed to it like you could see me point, but that's what we're going for. It's a tuned circuit. And back in the old days, let's put a line through this, that would be a variable capacitor. Nowadays, all the radios are synthesized and everything's done through a button and computerized and all that. But back in the day, we used a variable capacitor to change the resonant point of this circuit and select different frequencies that we wanted to listen to. So long live knobs. Any questions about that? That's kind of a confusing little tidbit. Don't say anything. Okay, moving along. Semiconductors. Well, if a conductor passes a flow of electricity easily and an insulator blocks the flow of electricity, then what's in the middle? A semiconductor. They're okay conductors, not great, but they can be doped up with various chemicals that can ease the flow of electrons through them, especially if there's a controlling current that is applied to them. There's a couple of different types of semiconductor components that you need to know for the test. One is a diode that allows electrons to flow in one direction, and then there's a transistor that is kind of a variable resistor that's controlled by current. It's kind of a weird device, and we'll get to that in just a minute. These things are composed of two different types of materials. There's always an N-type and a P-type material that are sandwiched together to create a diode. And then you have a transistor, which is two of one and one of the other to create a transistor. And we'll see how that works here in just a second. Okay, diode only allows current flow one way. It's like a one-way valve in hydraulics where a fluid can flow one way. You try to push it the other way, it stops the flow. The cathode is the more negative terminal, since we're talking about negative and positive. And the little arrow, really handy, it points to the current flow through the diode in conventional flow. Okay, from positive to negative. An LED is nothing more than a diode that emits light as one of its properties. This is what would be called a rectifier diode. It's commonly used to change AC into DC. The power supply that's going to power your rig has rectifiers in there to cut that AC wave down into a just to DC. The next type that you see here, that's a Zener diode. A Zener diode has some other properties that are kind of unique. And without getting too deep down in the weeds, it's very handy for setting a voltage. It's a voltage reference. It has a breakdown point that is set at one certain voltage and one certain voltage only. So it's very useful for creating a regulated voltage. The next one is a Schottky diode, which is, it's kind of like a rectifier diode, but it has some other properties which are handy. It has a better recovery time and lower capacitance. I said earlier that there's no perfect component. Well, it turns out that inside each one of these little diodes, since you have two little tiny plates together, there's a little bit of capacitance there. And those Schottky diodes reduce that capacitance quite a bit. But main job that we're concerned with is it turns AC into DC because it only allows a flow of current in one direction. Transistor, well, again, it's sort of like a current controlled resistor. It has three terminals. The emitter, base, and collector. You can see here that it has a little arrow over here on the right-hand side that's pointing out. That is an NPN transistor, meaning that this terminal is made of negative material, the base is made of positive material, and then the collector is made of negative material. So NPN. The mnemonic to remember which it is, see the arrow is pointing out, NPN, not pointing in. Cute little mnemonic there, not pointing in. If the arrow were reversed and pointing in, a PNP, where this was a positive, a negative, and a positive material, it would be a PNP transistor. But NPN, the arrow points out, not pointing in. The characteristic that makes transistors really useful, whenever the base becomes more positive going in an NPN circuit, that turns the transistor on, and we can use it as a switch. You can also use a very small current on the base to create a very large current over here on the collector or on the emitter. And that's a little further down in the weeds. We're gonna skip an in-depth discussion on that, but if you want to learn about it, meet me afterwards. But making that little current control a big current, you can make an amplifier. You can make a small signal a very large signal. And that process is gain. A field effect transistor is a little bit different. It is a voltage controlled device instead of a current controlled device, but its operation is similar. All right, here we go again with the again, the bipolar junction as compared to the field effect that we just looked at. Again, an NPN transistor, negative, positive, negative, and these are the names to the three terminals. But arrow points out, it's not pointing in. That will be on your test, kids. All right, the FET has its construction is different. It's made out of basically a bar of silicon that goes between the drain and the source, and then it has some type of an impurity or different type of material that is adhered onto the side of it, and the current flow between drain and source is changed through a change in voltage over here on this side. That's different from the junction transistor that we just looked at, in that it was current controlled. This one is voltage controlled. And I know that the difference is probably a little hard to fathom right at the moment, but hopefully it'll become a little more clear as we move along here. All right, integrated circuits. What in the world is an integrated circuit? Well, they give you a picture here of a Motorola part, and it's kind of hard to tell because it's upside down, but this little 7643 right here, that's a date code. Means it was made in the 43rd week of 1976. So again, they could have used something that was a little more up to date, but this is actually a logic gate. But an integrated circuit is a lot of transistors, a lot of resistors, all packaged onto one substrate, stuck into a package. In this case, it's an epoxy package, and they bring the legs out to the side. They do different purposes. This is what's called a logic gate, which means that it responds to zeros and ones, positive voltages or no voltage. I think that's an AND gate. The schematic symbols are different for each type. They give you a couple of different ones here. Here we've got a flip-flop latch, clock latch, which is a memory element. And down at the bottom, they have what's called an operational amplifier. And you'll see these symbols. This is digital type circuitry. This is analog stuff, like more what we used to see in radios. The schematic symbols usually use U for a designator, whereas resistors were R, capacitors were C. Integrated circuits, that's usually a U. Protective components. A lot of jokes there, but I'm going to avoid them all and say that these are very important to you. Um, a circuit breaker is basically a resettable fuse. It's non-destructive, can be reset, reused, whereas a fuse is good for one trip only. And once that has broken, then there's no resetting. It has to be replaced. Schematic symbol is F typically for a fuse, CB for a circuit breaker. These are the things that in an overcurrent situation, a fuse will blow. And there are as many different types of fuses as Carter has pills. They are rated in amps. And you always want to replace a fuse with the same type of fuse. If you have one that blows, both in rating and in type. If it's a fast blow, it needs to be replaced with a fast blow. If it's slow blow, it should be replaced with a slow blow. You can get away with replacing a slow blow with a fast blow as long as the current rating is the same, but it really needs to be the proper one. All right. Switches. Switches are actually what breaks a circuit or makes a circuit. They're used to interrupt the flow of electricity. This is just like the wall switch on your wall, where you have a load and a power source, wires and a switch in between. Each circuit defines one of the poles of the switch, and each position is called a throw. Well, what the heck does that mean? If you look over here on this side, on the right-hand side, you see a single pole, single throw switch. Well, that means there is only one circuit that can be changed, and there is only one source and one destination. Here we have a single pole double throw. This would be like a three-way switch in your house, where you have one source and two destinations, and you switch in between them. Well, double pole, double throw is just like it sounds. Two sources, each one selects two destinations. And you can have four pole double throw. You could have, various combinations of terminals in these things. But these are the symbols that you're most likely to see on like tests and things. So single pole, double throw, single pole, single throw. And a push button looks just like its function. The connections would come off of the sides here, and whenever you push the button, it completes the circuit. There are different types of push buttons. There's momentary, there's push on, push off, all sorts. Okay, relays. All right, we talked earlier that whenever you pass a current through a coil of wire that you create a magnetic field. Well, that magnetic field can be useful for more than just creating inductance for a radio. You can also use it to move things. If you're just moving an armature or moving a bolt or something, I just completely lost my train of thought. Anyway, you can use that magnetism to move a switch for you. And that's called a relay. And this is really handy whenever you want to isolate circuits. For instance, if you had a expensive computer that you didn't want to, that you wanted to use to control a much larger load, you could use a relay to isolate that, because the coil, let me draw you a little coil here, show off my art skills. We had a coil here that we used to activate this relay. Whenever we passed a current through the coil, it would pull this armature down and move the switch from the normally closed side down to the normally open side. Okay, so these could be completely different circuits isolated from one another. And the other nice thing is that you can use a small voltage here, a small signaling voltage applied to your coil here, and use it to switch a much larger load over here on the relay, on the contact side. Just like we had the double pole, double throw switches that we saw on the last slide, same thing applies here. You have relays that can have multiple terminals, multiple poles, and a very handy little device. There's some guy out on the internet that's actually built a computer with relays. It's insane. Look it up. Other circuit symbols that you're going to come across. Well, I would be sure to know LEDs and rectifiers over here. These bridge rectifiers you'll see quite often. And of course, here's our NPN pointing in bipolar junction transistor, and here's our NPN not pointing in. FETs. These other MOSFETs over here are a different type of FET, but be familiar with those. Again, that's just the symbols that we use in our schematic blueprints to describe circuits. Does anybody need a break, or can we move on? Can I get a thumbs up, thumbs down? Is that thumbs up break or thumbs up move on? Thumbs up to move on. Yes, okay, here we go. Types of radio circuits. All right, a transceiver is a transmitter or a receiver in a box. That's probably 100% of the radios that are sold these days. Back when I started, yawning's not allowed. Back when I started a long time ago, they were separate. You had a receiver on one side and a transmitter on the other, and a power supply that was keeping your toes warm, and with a transmit receive switch in the middle. Well, nowadays they're a lot fancier than that, and they automatically switch. But you see a basic transceiver, everything that's in the little dotted lines there are the components of the transceiver. The transmitter that generates a radio frequency signal, a receiver that receives it and breaks it down into information that you can understand, a power supply down at your feet that powers the whole mess, a feed line to your antenna. And that's the whole radio system with a transceiver right there in the middle. Exceiver being the abbreviation. A TR switch, or a transmit receive switch, is what switches between the transmitter and the receiver. Nowadays, it's inside the transceiver itself. Transceivers are single duplex, which means you can't talk and receive at the same time. And the TR switch is what selects whether you're receiving or transmitting. A repeater, on the other hand, has a receiver and a transmitter that are linked together. And there is no TR switch, because what's being received on one frequency is being transmitted out on a different frequency simultaneously. They share the same antenna most of the time, and there's a handy device called a duplexer in the middle that keeps the transmitter from transmitting into the receiver over here. The thing to keep in mind here is that the transmitter and the receiver are tuned to two different frequencies. They're not on the same frequency at the same time. Okay, so the receiver receives the signal from the antenna through the diplexer. The information comes out of the receiver, goes back over to the transmitter, and is transmitted back out, usually at a higher power level and with a much higher antenna, so that you can get a much more distant signal. So your handy-talkie is going to be received by the repeater, and it's transmitted back out with more power. Okay. Radio communication requires two things. You got to have a transmitter on one end, you got to have a receiver on the other, and something is transmitted in between, either voice or code or data. Something is sent in between the circuit. And if you start with a basic radio wave, there's certain things you can do to it. You can make it start and stop, for instance. If you start and stop it, that's code. If you change how big it is, how large it is, the amplitude, if that changes with information, then that's amplitude modulation. You can also change the frequency of a wave, and that's how we end up with frequency modulation. The information is the same. The method that it's transmitted is just slightly different. Make sense? All right. Okay, receiving. The radio wave induces into your antenna the information that you want to pick up. Now then, your receiver is getting a whole great big wad of information forced into it all the time. Big, vast part of the spectrum will actually make it down that antenna, down the lead wire, and into your receiver. When that happens, we have to start filtering things out, throwing out the things that we don't want to hear, and focus in on those things that we do. It extracts the information that we want to have. This could be easy, this could be hard. There's very simple radios. Think of the crystal radio that everybody built in 7th grade in science class, versus the latest, greatest $10,000 radio that many of you have bought already. But it's kind of like how sausage is made. The result's great. You don't want to know how it all goes together, but we'll go through the basics of it here. Filters are circuits that they can do a lot of things, but basically what a filter does is it picks out a small slice of the spectrum that you want to keep. There are low pass filters, which means, guess what? It filters out everything but the low frequency portions of a signal. There's high pass that passes the higher frequencies, and there's band pass that passes frequencies in a limited band. There's also band stop, which means that it basically at a particular frequency, it stops the flow of current. And Peter Laws wants you to know that he does not have a $10,000 radio. Oh, there we go. There's the types of filters right there in front of me. If you look at the graph here, and they're calling it signal passed, but think of this as the voltage or the height of a signal. The cutoff frequency is the point at which half of that signal goes through. Okay, so we would say that this portion here that's in the reject section down here, this is attenuated or reduced logarithmically. Think about that. I'm not going to torture you with algorithms. That was somebody else's job. And then the frequencies above that half power point are passed. This is the essence of how radios function. If you see the band pass here, and again, this bottom axis here is frequencies from low to high. You can reject everything but the stuff that's in this passband, and that's the secret sauce that you want to keep. Now then, the trick is, how do you make this narrow enough that only the frequencies that are coming through are a voice that you want to hear? And we'll talk about how we work that magic here in just a second. But a high pass, again, it passes higher frequencies. A band pass passes some discrete frequencies that we're interested in. A low pass filters out the low stuff, and a notch rejects everything that's in the pass band. This high pass is really handy with microphones. If you guys remember a 60 cycle hum on a PA system, that's what high pass filters filter out. Okay, now then, we know how to generate a radio wave. We're going to say we do. How do we get the information out? How do we encode that information on a radio wave that we want to transmit? Well, that's what modulation does for us. If we can turn it on and off, that's Morse code. If we can change the frequency between two discrete frequencies that we agree on, that's something called radio teletype. Speech, of course, is those frequencies between about 300 hertz and about 3000 hertz that we want to hear. We can add that by modulating that radio wave that we want to create. So amplitude is one thing that we can change about a wave to contain information. Frequency, FM, we can change, or phase, which now there are uses for it, like there's a digital mode called PSK31, and there's a whole bunch of digital modes that are descended from that vary phase. But I don't think, unless they've changed the test, I don't think there's much they talk about that for questions. Okay, how do you add that information? Well, the little circuit black box that we use to add that information is called the modulator. The modulator is what adds the information into the wave that we want to transmit. A demodulator does the opposite. It takes the wave that we receive, it throws out the radio part that we don't care about and preserves the information that we do care about. So modulators add information, demodulators recover it. Changing frequency. There is a device that can take two different discrete radio signals and mix them together. Process is called heterodyning. But if we have one frequency that's coming into our radio, let's say it's 1 megahertz plus 1,000 megahertz. So 1,000,000 hertz coming into your radio, sine wave coming in. And it goes into this device called a mixer. And on another part of the mixer, this black box, there is a 1,000,000 hertz, 1 megahertz signal coming in. Then the mixer actually generates two output frequencies. One is the sum of the two frequencies that come in. One is the difference that comes in. Well, how is that useful? Okay, we're at 1,000,000 hertz coming in minus our other signal of 1,000,000, we're left with 1,000 hertz. How is that relevant? Well, 1,000 hertz is right in the middle of your hearing. Okay, so that's how we can take these huge, giant frequencies, mix them with another frequency that's generated in your radio, and the mixer itself pulls out something that is intelligible. Does that make sense? So a mixer takes two signals in, one that is coming from the sky, one that's generated within the radio, and intelligence comes out the other side. Now then, I also said earlier that there's no such thing as a free lunch, that there are, that none of these components are perfect, but for our purposes here, good first approximation, that will work for you, okay? So the things that are coming out of it are called the mixing products. The main ones that we're worried about is usually the subtracted product. A multiplier is a different kind of device. And I don't know why they put it on this slide. It's a different type of device, but it multiplies the frequency coming into it by a set integer. It can't be a real number. It has to be an integer. Usually a doubler, tripler, quadrupler. You get the idea. Okay, sensitivity is how well a receiver can detect signals, not just weak signals, all signals. The more sensitive it is, the smaller the signal it can receive. Selectivity, on the other hand, is how narrow can we get that filter passband. Okay, what we want with selectivity is to capture those frequencies within the passband and reject everything outside of it. So the more selective it is, the tighter and straighter that filter is to reject everything outside what you want to hear. A preamplifier, I'm going to preach here on my soapbox. Preamplifiers are wonderful things, and if you have one in your transceiver, you should probably leave it off most of the time because it amplifies everything that comes into it. Not just those things that you want to hear. It not only amplifies the signal that you want to hear, but it also amplifies the background noise. So many times it can cause you more harm than good. So just keep that in the back of your mind. A preamp goes in between the antenna and the receiver. It can help you make a rather dead receiver more sensitive, but again, it not only amplifies the signal you want, it amplifies noise. A transverter is different than a transceiver. A transverter is a device that allows you to transmit on a different frequency than your transceiver is designed for. It basically takes, well, the typical examples at the bottom. If you look on the very right over here, you see 222 megahertz band is pretty high frequency. What a transverter does is take that 222 megahertz and converts it down to 28 megahertz for your transceiver to operate with. Okay. There's so many of the newer radios that include every band from DC to daylight that transverters aren't used as much as they used to be, but it basically shifts that frequency down to where a standard radio can receive it. It does both receiving and transmitting, but it just converts the signal from your transceiver for a band that you didn't have equipment for before. It's kind of like an add-on accessory. Make sense? Anybody? Anybody? Can I get an amen? All right. Wow, that's the end of week 3 already. Gosh, you guys are smart. Does anybody want any supplemental stuff?
Your microphone's off, Bruce. There you go.
Yeah, as if this weren't enough.
Can you say clear as mud?
Mud.
Hey, don't insult the teacher right in front of him.
Mud.
Great job. You did a great
Yeah.
job. It's just tough.
Just remember that mud settles and in a week it gets clear.
That's
Good.
right. Guys,
That's-
it's really not as difficult as it first sounds.
No.
Ken did a beautiful job of it. And I think the biggest thing you're going to find is that once you sit down and you start component by component looking at them and figuring out exactly what they do and seeing it in application, then the light bulbs come on for each one of them. And you can see what they do. You know, remember the potentiometer. You know, you use it all the time, you know, in stuff that you got when you reach in your car and you turn on your radio knob or something like that to turn up the volume.
Yep, the one that
That's-
goes to 11.
There you
How
go.
is that different than like a rheostat?
Same thing.
It's not. it's the same.
Okay.
Rheostat's a high power potentiometer. Sort of.
Says the engineer.
Yeah.
It's one of them electric
I'm
things.
just gonna
Yeah,
sit close
yeah.
to Bruce.
I'll have her explain it to me.
Right.
Guys, I will tell you that don't be afraid of this. The test, the most that you're going to have was what, Mark, was it 5 questions?
I mean, on this topic.
Yeah.
Do they give you diagrams on the test?
Yes.
Yes.
Like
you
circuit
get
diagrams?
diagrams and it will say, what is part C5?
It's a capacitor.
It's capacitor number 5.
That's
There
there
you
you go.
Or it will say, what is part D?
That's a diode, right?
Well, no.
Oh.
If you got A, B, C, or D,
Yeah.
and they'll say, what is part D? And you say, it's a resistor, and that's what it is, then you got it right. So, the questions are not going to be, set up. It's like this. If you've studied, the questions can't fool you. If you haven't studied and you sit down to take the test, you're going to fail it.
Ken, why don't you show on that simulator, you've got some of those pieces, and that might be.
Is that up on screen? I guess it is on screen.
Yep.
Yeah.
This is a neat little circuit simulator that's available at fallstad.com. He has dozens of little circuits already worked up for you, but you can actually play around and see how these components interact.
What was the name of that?
Fallstad.com.
Falstad?
Yep, it's up on screen there. And I think Mark has a link on the SCARS webpage under Homebrew, Mark?
Yeah, we'll put it on the class, the tech
Okay.
page, so it'll be there for the class.
There you go. But it has animation where you can see the effect of switches, for instance, how it interrupts circuit flow. You just click on the switch and it'll toggle between open and closed. If you select a component and hit edit, you can change its value and see how that changes current flow, for instance, through a battery. And now we're going through here. It also illustrates both parallel and series circuits, as you see here. If you can just isolate just this outside edge here, you can see a good series circuit. And if it's broken at any place, it stops the current flow. It also illustrates parallel current flow. It does a lot of things. And if you go down to the section that says index, it will bring up a list of different simulations that he's already got designed for you. And probably the ones that are under basics and AC circuits are the ones that will be most applicable to what you're doing right now. And filters to a certain degree too. Excuse me. Transformers down at the bottom. It shows how changing the ratio of the transformer can change voltages. It's just something to play with. And as you get further and further into electronics, especially as you go towards the general test, you can create some of these circuits and actually see how changing values changes results. And it's very handy little thing.
And when you decide to progress on past your technical technician
will.
license to go to general, it's going to have more meaning to you, definitely.
Yeah, the circuits in the book I studied from was It's a kite and a string and a key.
Say that again.
No
This-
clue.
The circuits in the textbooks that were in my, when I was studying, that had a kite and a string and a key.
But those are in stone.
Yeah, right. Prehistoric.
Dude, high homage.
Oh my gosh.
Beware of high ohmage.
Danger, high image. Yep.
If anybody has any further questions for me, or if you wanted to dig into this further, or you have questions down the line, contact me. I'm kendallg@yahoo.com. I also haunt the SCARS Facebook group, and I don't post much, but I'm there.
Yeah.
They let me out of my introversion cage twice a year to do these classes, and but I'll be watching.
Pretty sweet.
Dan, could I make a comment?
No.
Okay.
Yeah, go back to sleep, Bill.
Okay.
Go ahead, Bill.
Well, I'm just going to say on one of your slides, the one that inductor symbols,
Uh-huh.
I noticed there were two symbols for two inductors. One was an air coil and one was wrapped around a toroid. And the picture below them are those are the pictures, but the symbols were an air round one and a variable one. That didn't want people to think that a variable inductor was a toroid wrapped inductor.
Mark, fix that.
I
Okay.
caught that. Yeah, I caught that.
It's not on the test.
Thank God.
No, it's not on the test, but. Oh, and you said you didn't know where I came from. Current, the symbol I.
Yes.
Well, it according to my telephone, was a French. It came from French phrase "intensité du courant," which meant current intensity in French, and it was.
Oh, that
used-
explains it right there. It's
Yeah,
French.
it first was used by Ampere, Andre Ampere in 1820. And he used it, and it was used heavily in French and in France, and then it went to Great Britain, where it became standardized.
That sounds like fake news, Bill.
Yeah, it's sort of
Probably is.
believable.
Guys, just
Okay.
remember this. It's not like the French guns that were only dropped once and never used.